Hi, everybody. I'm Rachel Rayner. I'm part of the marketing team here at Bluebotics, which is part of the Zappi group of companies. I would like to welcome everyone to this session of the Future of Electrification. Thank you so much for joining us. Now, please remember that this session is also being recorded and will be available to watch on demand following the session. If you have any questions at all, please add them to the Q&A. You'll find that tab to the right of your screen. Note that your questions will be sent privately and we'll read them out at the end of the session. With that, I would like to introduce our speaker for today. I'd like to extend a very warm welcome to Christian Stausch from Hydac Group, who'll be speaking today about scaling off-highway electrification through modularity and pre-validated systems. Welcome, Christian. Please take it away.
Thank you for the kind introduction, Rachel. Good afternoon from my side. My name is Christian, as Rachel mentioned, and at Hydac Group, I'm responsible for the product divisions or the business units Enduro, which is our electric drive division, and e-mobility solutions, which is our kind of engineering partnerships division. Today, I want to talk about a very practical question on how can we help scaling electrification in off-highway machines, where volumes are typically low, applications are diverse, and of course, cost pressure is high. My answer may be not full, but it's quite fairly simple. It's about modular product platforms, pre-validated systems, and the right partnerships. But before we go into the details of this answer, please allow me to give a very brief introduction on who we are before starting that. So, for those who don't know us, Hydac is a Germany-based family-owned company, but with a strong global footprint. So we're 11,000 people around the world, 50 subsidiaries, and also 50 is a good figure. We also are experienced in more than 50 industries today, much of them in mobile applications. When we talk mobile, when we think mobile, we're often trying to think in machine functions, actually talking about steering, braking, propulsion system, thermal management. This is from our point of view, the language of the partners we work with, and we're trying to think in that. And that's also the baseline of my presentation, that I'm trying to show the challenges of the electrification in terms of talking about functions, talking about subsystems, and not give let's say, too much of a product perspective, even though we are a product manufacturing company. In the end, we sort ourselves in terms of kind of 5 product platforms. Most known, clearly, we are for hydraulic systems and components. This is the founding spark of Hydac, especially also in filtration. We do a lot of thermal management, so fluid conditioning, but also motion control has been an important part, starting with electronic systems architectures. And the most recent technology field that we're working in is the one that I am responsible for, which is electrification and alternative drivetrains. From my point of view, of course, the most interesting one, and I guess there's some of you sharing that view. Most interesting, but maybe also most challenging one, if we look to the next picture, that kind of tries to describe the situation. I mean, we're trying to reach the goal of a zero emission or at least local zero emission world, also for mobile machinery, for off-highway applications. But we're clearly still not there. We did not reach the goal. We are about to reach the goal, but the way there is it's not an easy way. The conference is entitled From Hype to Reality. So let's have a look and start with a simple question. Where are we today on the path from hype to reality? I guess many of you have seen that picture, that curve before. This is the so-called Gartner hype cycle. And I think we have passed that peak of inflated expectations, probably end of 2023 to end of 2022 to end of 2023, when electrification was the overall dominating topic at all big trade shows, at all project discussion. Everybody was talking about electrifying everything and doing that immediately and so on. And I think we also, in the meantime, moved through of disillusionment. So I think today we are already, and this is not only hope, I'm an optimistic guy, and pretty sure that many will share that view on that, climbing that slope of enlightenment towards, the so-called plateau of productivity, where it is not about electrifying everything for self-purpose, but really doing that for hard reasons like total cost of ownership, like productivity of electric machines. And we're going to see throughout the presentation that there is use cases that actually cover these topics. So the question is, why did we need to go through that through of disillusionment? And I have some 6 quite simple answers just to make the ground for the further discussion. The first one is, of course, systems complexity. The system complexity for electrical machines is increased, both compared to conventional machines, but also compared, for example, to electrical passenger cars. So there is more complexity in electrifying an excavator, a wheel loader, a tractor, than in having a conventional vehicle. Then, of course, we're talking about quantities. The quantities are way smaller than we have today in other segments. And this also goes along with cost, of course. It's all about economy of scales in the end. If there is not that much quantities and the components are a bit more expensive or still way more expensive, then it's all up added with complexity and more expensive machines. So when we're talking today's projects, we often talk about cost parity as a target for the next generation of development of electrical machines. But when you look into electrical machines that are in the market today, you still often have factors of 1 point something to even up to 3 times the cost of a conventional machine. This, of course, is not a long-term stable way, and we have to find on how to accelerate the economy of scales in order to get out of that dilemma of low quantity, high cost solutions. Then, of course, electrification in off-highway is not about emotion or being green. It's typically about off-highway machines are bought because they are production machines. So it's about productivity, total cost of ownership, and there has to be a business case behind. And of course, one solution to solving that dilemma would be a starting help with incentives and funding opportunities. This is just simply not there, and it hasn't been really around in most parts of the world over the last 2 or 3 years. And last but not least, nobody wants to hear that argument about the passenger cars, that the infrastructure is not working. I think many of you are driving electric cars and will agree that electric charging works perfectly for passenger cars, but the situation is a bit more complex, of course, when it comes to electric vehicles. But nevertheless, this is reasons why we have went through that through of disillusionment. But I said I'm an optimistic guy, and I have some good news, and I think many will share that the electrification is coming. There is, when you see these kind of applications, like really, really large machines being electrified, mostly for total cost of ownership reasons, partly, of course, also because of ESG targets, but there is big deals, a lot of money in electrifying these machines. So there is no real physical barrier in doing so. It's just a matter of the business case. And if the big ones are getting electrified, then everything can be electrified. But of course, it's not as easy going as I indicate here, but there is some challenges to that. And of course, part of the challenge is speed and it is cost, especially from a European perspective. I think we all agree that we need to be faster and we need to be more cost efficient in the long run to really be able to develop stable electric machine portfolios. So the question then is, what does hinder us from being fast and from being cost effective? Of course, there is, again, a lot of answers to that. Some of them are political answers. I don't want to dig into that. I just want to dig into what can we do and how can we solve the problems with speed and cost. And one answer, again, to that, I said it before, might be systems complexity. Just have a look to that picture. Maybe starting with the left-hand side, this is a schematics of a conventional diesel powertrain, where you have the You have a lot of functions directly connected to the DSO. Typically, you have a quite direct drive, but you also have steering pump drive. You have the alternator. You have air conditioning, all directly connected to the diesel engine, probably via belt drives. So in this picture, the belt kind of acts as as a kind of mechanical systems integrator, actually. This is well proven in use, stable, robust for many, many years. It works pretty well. When it comes to electrification, of course, we want to cover the same functions as in the left-hand side of the picture, also in the right-hand side of the picture. We want to still use hydraulic pumps. You will have a traction drive. You have steering pumps because there is still hydraulics in steering. You have air conditioning, and of course you have some energy source. But now there is no belt anymore that is connecting all that components together. We removed the belt and replaced it by power connections and signal connections, which is bringing a lot of freedom, of course, because you are not tied to the engine speed anymore. You can separate functions. You can run different speeds. You can do things like start, stop. You can really be more efficient, be more fuel efficient, be more cost efficient in the end. But of course, this comes at the price of complexity. And this is something we want to dig a bit deeper during this presentation and also into solutions on how can we do that. But isn't there just like simple solutions, like looking on what is the automotive industry doing and can we do the same, like going to a package like a diesel engine? I have one example. This is an example of a highly integrated system. I think this is an example from BYD where you really have high integration. You have not only motor and inverter integrated, but you have the gearbox directly integrated. You have two kinds of power electronics, both the DC-DC converter and the onboard charger. In addition to the inverter integrated, you have the power distribution unit. So everything works pretty well. And you even have the ECU, or in this case, the ECU with battery management integrated. So only the battery is missing. Then you would have a perfect diesel replacement in just one integration. So why do not just do the same for the off-highway segment? Well, there is some reasons why this works fairly well. The first one is most of the passenger cars have a quite similar footprint or space claim for these kind of components. So from outside, of course, they look different, they differentiate, but from under the hood, there is like very similar architectures, and they all share the same goal. They want to optimize their consumption according to the WLTP cycle. So this is quite a clear optimization goal, and this allows for a lot of effort putting into engineering development, validation, and of course there's also tool costs related to such high integration. So this must somehow bring a return on invest, and this is usually done via quantities. Now let's have a look at our market. Typical field of application in the off-highway market. So there is starting with like pleasure boats and work boats on the one hand side, going via agricultural machines, construction machines, special machines like GSE machines, but also sometimes semi-stationary machines and things like that. And all of these applications, of course, have different mission profiles. They have different space requirements. They have different environmental requirements, different power requirements, and in the end, none of these applications alone have really high quantities. So that highly integrated, high quantity solution might not really work, especially in an industry that is well used to having highly customized powertrain systems, as everybody who has been working hydraulic knows pretty well, that there is a lot of customization in these kind of applications. So, of course, skipping customization would be part of the solution, but maybe there is also a better solution. And one answer to that might be modularity. For example, just picking out one component example, looking into motor technologies. There is like two poles of motor technology. I wanted to put it like this, or two ends of the spectrum. Again, on the right-hand side, you have that automotive technology I've been showing before, When it comes to stator windings, for example, they have a technology called hairpin windings, which allows for a very high copper fill factor. But whoever has seen a production machine for a hairpin automotive stator must have got the impression that this is a production machine that is very effective and has a very high output, but flexibility is nothing that works with these kind of production machines. And this is typically for having like 50,000 plus motors of the very same winding structure. Then you can do such hairpin winding with the benefit of that very high power density. On the other end of the scale, there's industrial drives, mostly in stationary applications, where you have a very high variance. You have a lot of different applications. You typically do not have always the same windings. In this case, you have round wire windings, which typically results in a lower copper fill factor, but with much more flexibility, from manual winding to also automated machine winding in higher variances. And also this can be produced in high quantities at a reasonable cost, actually. But as we all know, mobile application is something where power density, torque density is quite important. So what we are trying to do, and I think most of our competitors and everybody in the mobile world also is trying to sit somewhere in between, combine the best of both worlds, and try to find high power density motors with based on flexible technologies. In this case, round wire technology, of course, as most of the guys do, and still achieve by special winding systems a high power. Not only, but being part of that, a high power density. And yes, power density is key. We cannot sacrifice all the flexibility to power density. And that's where modularity comes into play. Just to give an idea on how that works, typically modularity means you have some standardized technological core. This is the part that you don't want to vary from project to project, because there is a lot of effort put into that. There is tooling related to that. There is a lot of simulation, validation related to that. So everybody coming out of the hydraulic space knows it as for example, as a pump, where you have the rotation group of the pump. For motors, it's quite similar. It's the rotor and the stator. Once developed, you do not want to change it from project to project. But application and variance does not necessarily come from the electric core part of the motor, but rather from interfaces, from cooling, from having different set points in terms of voltage and at speed. And this usually can be controlled by varying the length of the motor, varying the windings of the motor, varying the cooling jacket of the motor. So this is where modularity comes into play. And of course, in the end, you also need a production that supports that kind of modularity. But if you bring those things together, you end up with a very modular portfolio. I do not want to go into the details, as this is not a product presentation, just to give you an idea of what is possible with that kind of modularity. So typically, out of 5 different frame sizes, 2 cooling principles, you can cover in every frame size 4 voltage classes. So you can, for example, have let's take a 30 kilowatt motor, because it makes sense in every voltage class. You can have that in 48 volt, which is kind of a boundary case. You can have it in 96 volts. You can have it in 400 volt, in 800 volt. The same motor, same technological core once developed, but varied throughout different applications. And of course, with a lot of projects come a lot of mechanical interfaces, which ends up with just having a small variance in the core, but in the end, more than 160 different application-driven product types. So part numbers, whatever you want to call it, different types of motors in the game. And of course, this is only motors. You can do that for every other component that you find in the electrification space or in the off-highway space in general. And why does modularity help? Not only on complexity, but also on being fast. I will give you an example of that with the next slide. So this is 2 applications that are as different as they can be, probably. One, a clear off-highway application. On the left-hand side, this is a so-called eKbot. This is an autonomous farm robot, tractor size, so roughly in the 200 kilowatt class. And this is all about autonomy and productivity. So this is a diesel electric vehicle. It's not about zero emission, but it is about, as I said, autonomy and productivity, where electrification really helps. I do not want to dig into that in detail, just to show what this machine stands for. Well, and on the right-hand side, this is just a simple bus at first sight, but the bus comes with a, let's say, a new problem to solve, because there is some new regulations upcoming in the EU. It's not that easy to use the bus air conditioning anymore, because with that new regulation, you often don't find the right AC systems in conventional applications. So what you can do, and this has been our solution to that, is to use a high voltage generator, replace the conventional compressor by a high voltage generator, generate a high voltage system for a conventional diesel bus, and by doing so, supply a high voltage propane AC air condition system. So this is a retrofit option to get along with that new regulation. And this is done by using a diesel electric system. And this is the similarity actually of the two applications, because both of them are diesel electric, and both of them come with very special challenges. Diesel electric without a battery. Without a battery means that you have a very, let's call it, from a control theory point of view, a very stiff DC link. And that means you need, on the one hand, high dynamic voltage control from a generator point of view, but you also need to stabilize the DC link, because if you do not do so, with every load change, the inverter will probably see an over voltage or an under voltage error, and the system just stops. This is the contrary of productivity on the left-hand side, but also when you think about an air condition. And for those who know Deutsche Bahn, this is a Deutsche Bahn bus. Deutsche Bahn has been very famous on their trains for non-working air conditions. Of course, we want to avoid this. So this means you need to have that DC link stabilization and good voltage control. And once you have application experience in modular products on the left-hand side, you can just do a carryover to the right-hand side and be fast in projects. This is the baseline of what I wanted to share with that example. So what does such a system typically look like in reality? It's not as compact as you have seen it on the machine, because here it is a lab example. And you see here, let me explain the architecture. So you see here, in the end, an electric system for driving a rotating shaft. So quite a simple system, but there is some things you need to do for that. The rotating shaft is, of course, part of the motor. You need an inverter to do that. You have a battery in this case. Everything is high voltage, so it's liquid cooled. You have a power distribution unit with all the fuses and contactors. You have an onboard charger charging the battery, and you have some HMI and some machine control ECU. And the reason why this is mounted on such a wooden table, I will show in a second. So the question is then, I've been talking about being fast, and I've been talking about one problem is complexity when it comes fast. So this should be quite a simple system, right? Looking at the system's architecture, this block diagram looks quite manageable. I mentioned the components before, but this is a part that is often underestimated, because especially when something like that is done for the very first time, when you look into the components, every of these, let's call it major components in the system, has its own so-called states. So it's not just simple on-off, battery on, battery off, but there is some states, some software-based states for the battery, like at least drive and charge. But everybody who knows, who is working in development of such systems, knows that there is some more. states with this. And the same is, of course, true for the onboard charger. And you see it's not the same states as the battery states. And the same is true for the inverter, and even the DC-DC converter has different states. And of course, the states are not standardized. There is some approaches to standardization, but let's be honest, nobody really is implementing standards 100% in every detail. So there is always something that is non-standard. And if you look into the components, these states are, of course, all interconnected to each other. So there is a so-called state machine with transition conditions, and the component is moving from one state to another state when it gets the right CAN messages, or the right message, let's call it message, but in most of the cases it's CAN, at the right time to switch transition. And you see that even for such a, let's call it a simple thing like an inverter, there is quite a number of states, and just remember all the other components. Number of states, non-standardized, everything needs to be triggered at the right time to work with each other. And if it's not triggered at the right time, then there is an error state. An error state means the machine is not moving. Non-availability, this is the contrary of productivity. This is the contrary of good user experience. So there is a lot of potential for doing things wrong in this place. And of course, also on machine level, there is kind of states or sequences that you have to go through. Just give a simple example. This is let's call it a boot sequence from starting the key switch over working. Working is just 0.9 in all that sequence. And then there is again 6 different states for shutting down the system. So this is not just mechanical connection and a belt bringing everything together, and you activate the key switch, ignition is starting, and everything is done. More or less, let's say mechanically or highly integrated, but you have to really synchronize these states. When it comes to charging, just think of charging a conventional vehicle. Let's maybe do some oversimplification, just plugging a receptacle into that vehicle and refueling. In this case, it's even more sequence. And everybody who has been working in developing electric vehicles knows that charging, compatibility between different systems, between different chargers, batteries, off-board chargers, and so on, is often a pain point in development. Of course, we managed to get that robust, but there is effort related to that. This is what this is all about. There is always effort related, a lot of effort, more effort than with conventional vehicle. This brings in complexity, and this brings in cost, and that's hinders for being fast. So just a brief example on how this looks when everything works. The sequence is going quite well. Interlock is checked, isolation monitoring is checked, battery is there. So now you're going through all that states we have seen on the architecture slide. Everything is up and running. In the end, the shaft is turning. As simple as that. It's just about the turning shaft. So a lot of effort, a lot of things, of course, that can be automized or standardized, but it's work that has to be done. And just again, just to get some point to that, I do not want to go into the detail of the single wire diagram, but some of the secret sauce, what is let's say, a very pragmatic way of controlling that kind of boot sequences, startup sequences is, for example, shown here. You have the high voltage components on the lower right part of that diagram, and you see there is a bunch of relays here, and we just use the relays to have some dedicated K15 control, which means we can more or less in hardware just like mechanically control the startup sequences of these components. This brings in some robustness, and this brings in really control about the system. And just to give an idea of the system, because this also is a quite interesting application with a quite interesting use case. In this case, again, we're talking kind of a diesel electric system, but it's kind of separated in a diesel-driven truck with an electric trailer. So the question is, why should we have an electric trailer? It's quite a simple thing. It just needs to move up and down and carry dirt around. So why should we invest in an electric system? Well, let me just give a rough sketch of the use case or the business case behind. typically these trailers are long life machines. They survive actually three trucks during their service life. And every truck that wants to operate such a hydraulic trailer needs to go expensive post-production actually to have the right hydraulic system. So this is often not done inline, but it is something that is done post-production. So this is quite expensive. This gives just a very rough estimate, about 40,000 euro added cost per trailer lifetime when you talk about 3 trucks. So this gives you the ballpark on what you can do in improving something. And improving something in this case means adding a electro-hydraulic systems for several reasons, but one of the reasons, for example, is productivity. Because the lowering of the trailer works much faster if you do not rely on a single hydraulics line that comes from the truck, but you have a dedicated hydraulic system that you have under your control. And lowering faster, because you can imagine if the bucket is empty, lowering is just gravity lowering, which is pretty slow. But if you can somehow speed that up, this is an increase in productivity. And these machines are typically, these trailers are typically used in construction sites where you have many of them carrying dirt back and forth. So having faster lowering means more operation per day, means more dirt moved per day, means increased productivity. Just as one example for a use case that maybe nobody's thinking of in the first place. So coming back to that complexity topic, where is that complexity that I've been talking about? Well, in the end, complexity is in knowing the system and knowing what can go wrong. Of course, you should have an idea of the functional specification of what you want to do. You should especially know the state machines of your components because they differ, they are non-standardized. You should know the CAN protocols. You should design the system such that you can keep control. Remember the K15 example. And in the end, of course, it's testing, because there is things that are not expected in the beginning. And that's the reason why you have seen the system mounted on a wooden table in the first place, because you do not want to start test the first time when you're on the machine. You want to cover that in the lab where you can be very much more reactive. So component knowledge in early testing, this is the message I want to bring here, avoids late iterations in the projects. Okay, and just to give you an estimation of the efforts I'm talking about all the time when it comes to system integration and software efforts, we have again to compare 2 different architectures. On the left-hand side, again, the conventional vehicle architecture, on the right-hand side, an electric vehicle architecture. And when we look into the drivetrain alone, what most people think about when electrifying and what might be from a functional safety standpoint of view, of course, the most challenging part, then just isolate the drivetrain comparison. We say it's about 1 point something, maybe up to 1.3 the effort. This is the experience we have made throughout many projects that you have to put into creating a working, tested electric drivetrain. But just remember the picture with the diesel engine in the beginning, the high voltage or the electric architecture, which is also true for low voltage systems, is much more complicated or much more complex than the conventional diesel engine architecture. This typically results in an effort that is 3 to 4 times the integration effort you have for an electric machine compared to a conventional machine. So this brings us to the conclusion that we should start reusing stuff. We should not start always from scratch. And again, modularity could be one solution to that. This is what we are trying to do. We're trying to modularize software to decouple, for example, the communication, state machine based issues that are component bound from functional parts, like, for example, a ground drive, a thermal management system. So the idea is to have different software layers with drivers, with functions, with overall vehicle management, and that you can really reuse those building blocks. In best case, you can use the same charging software block that you have for a pleasure speedboat and for a reloader. This is then really reusability and modularity that helps us being fast and saving engineering costs. But we've been talking about some struggles. It's not only about the protocols, but often there is some things not working in the first place. And most of them are not related to machine types. So they are more or less related to the underlying systems architecture. The interesting thing is that when you look into, let's say, an oversimplified systems architecture for an electric system, you compare those, many of those machines have quite similar systems architecture. So there is a lot of similarities. They share, so to say, the same architectural basis. It's when talking about battery electric, of course, it's always a battery, a charger, a DC-DC power distribution unit, a machine controller, an inverter, a motor, maybe more inverters, more motors. Sometimes it's one battery pack, sometimes it's 5 battery packs. It depends. But the underlying architecture is something that is often quite similar. So then this brings up the question, if we want to be fast, remember the picture in the beginning, complexity and speed. Isn't there, or cost and speed, isn't there a way through, of course, a well-designed system? Being fast cannot mean getting rid of or letting loose with quality design. So there is some stages you have to go through. You start on the left-hand side with your system design. You have to go, even if you have an idea, you have to go through implementation. And really important, I said before, is verification, testing of the system. So the question is, isn't there something like a fast lane? And actually, I have mentioned the fast lane in the title of my presentation. Of course, there is when you have similar architectures, then reuse is again the keyword. So pre-validated systems that can be reused is something that brings part of the fast lane. So the idea is to have similar architectures with the same components that are tested working together with the same software building blocks that are tested working together. And you can have some, of course, this will never be a machine. This is always like an 80% solution. And you have to go the last 20% in a machine in application engineering. But it saves a significant amount of time in the development process if you just rely on a pre-validated architecture. And this is an example of such a system. For example, this is, of course, again, modular, because we're not talking automotive. We always need some modularity. This is a 48-volt system. Therefore, we're talking about only up to 24 kilowatt hours. You have different charging options. Of course, you could have more, but this is what turns out to make sense in, let's say, many applications in the market. You can have several kinds and numbers of electric drives. And of course, what glues everything together in the end is the software, the ECU, the control system with integrated power management, error management. So all the things that need to be developed step by step when you start from scratch. This is the idea of a pre-validated system. And of course, a power distribution that from an electrical point of view brings everything together. And then there's some auxiliaries and so on. So the question then would be, if everybody uses a pre-validated solution, what is the difference between the machines then? If everybody uses the same drivetrain, is then every machine the same? Well, that question could be answered quite easily when looking to the past, to the diesel engine ages, to the old days. Of course, the diesel engine did not bring the differentiation to the machine. What brings differentiation to the machine is, of course, the productivity of the machine, the overall vehicle software, the way the machine feels, the popometer, as we say in German, the robustness of the machine, but also the user interface. And in the end, of course, it's the service offering that an OEM brings to their end customers. So it's not a rotating shaft that brings differentiation to the machine. It's rotating shaft is just a necessary condition. Therefore, it is something that can be reused. So let's standardize what does not create differentiation and invest engineering time where it truly does. That's the idea behind reusing. And again, there is totally different fields of application where you can use the same system, starting with small, typical, very small machines. But also you can have, for example, like start-stop systems on truck-mounted machines, where you have conventional machines that want to switch off the diesel engine when they are working in an urban environment. And you can even have applications that you maybe do not think of in the first place when you think about 48-volt systems, like, for example, such a recycling shredder, which is typically a grid-based machine, but needs to move from A to B from time to time. And this is something that could be also handled by such a pre-validated system. So you do not need to have a small diesel or gasoline engine, but you can do this also in a zero-emission electric way. And this often opens doors for some of the fundings and things like that. So there is, again, interesting use cases for these kinds of systems. And of course, the world does not end with 48 volts, so you can do basically the same thing in 96 volt. Why? This is quite attractive because the architecture and the underlying components are often very similar. Of course, you need a different battery. In this case, we use an LFP battery, but you can scale up for example, the peak drive power up to 60 kilowatt. You rely on the same interfaces. You have to do some adaptations regarding to electrical safety because not every machine in the world can handle voltage between 60 and 120 volt as easy as a forklift can. But this is solvable problems, and you end up with systems and software architecture quite similar. And again, this is reusing. So everything done, right? Let's have a look at some of the reality. Session is called From Hype to Reality. So the architecture stays the same, but the challenges clearly do not. Here we have an example of such a system. It's again a truck-mounted system where you have a battery-powered PTO kit for a truck, so hydraulic power out of the battery, such like a start-stop system. I mentioned it before, but with higher power for 96 watt. And the challenge here, of course, is that the components are distributed across the vehicle, and that's often related to, let's say, EMC trouble. Let's have a look to the signals. This is a typical CAN signal scope recording, which looks quite okay. And now let's start the motor, and it looks like this. So this is something that is clearly not okay. This is violating standards, actually, that give limits to CAN levels, and it also ends up with error frames on the Cantor system not being stable anymore. Stable in the sense of there is errors that start that cause a switch off of the system that need a restart. So again, not robust, not available, not productive anymore. So not acceptable from a customer point of view. The problem here, the error frames, there is, of course, some challenges coming out of the vehicle, like, for example, you have long cables, and something that may not be underestimated is 96 volts is not 48 volts. So there is an increased voltage change rate. It's double the voltage change rate. This, of course, has an impact on EMC, on what's going on with currents, also on the ground and PE and so on. And what didn't help in this case is, of course, the first idea is this EMC stuff comes from switching. Switching is in the inverter, so just replace the inverter, everything will be. Of course, that did not work because it's a system-related topic. It's been about a lot of simple measures that everybody knows from textbook didn't really help in this context. So what helped in the end is going back to start doing a well-designed wiring topology, doing filtering where it makes sense, and having the conduit the correct CAN references in the end. So what this example shows that the EMC is not the often cited black magic. It's mostly about, again, early testing. I call it evidence-based system design. And of course, a lot of practical experience, which maybe comes close to black magic in the end. But this is something that is available. A lot of you have acquired experience. We have acquired experience. So this is solvable problems in order to scale electrification. Talking about voltage levels a bit, I want to keep that short because I think many of you have already discussed that or thought about that. This is, for example, a chart that shows voltage over continuous power. And the question is, when to use what? We have some rule of thumb for ourselves when we are asked on how to design a system. That is, we do not want to cross that line, that 500 amps line. Why? Because component continuous. We're talking about continuous current. Component availability gets lower. Everything gets bigger. Everything gets more expensive. So this is something we're trying to cluster like this. Below 20 kilowatt, it often makes sense to use 48 volt because it's extra low safety voltage. Everybody loves 48 volt. There is a space where 96 volt totally makes sense. Maybe that's something a bit different to what people have been discussing over the last years. Or a few years ago, when everybody was thinking like 48, a lot of people were thinking like 48 volt will be the small machines, and then you are going high voltage because of platform reasons. But 96 volts still has a significant cost advantage, not only because this is actually economy of scales, because it's coming out of the forklift market, at least the power electronics there, but also because it can be simpler. For example, MOSFET inverters do not necessarily need a liquid cooling system, so you can save system cost when going from high voltage to 96 volt in that segment. And of course, above you are in the high voltage segment. So what about pre-validated solution when it comes to high voltage? I wanted to put it like this. This is something that can be done, but the variance in high voltage applications is by far bigger than it is in low voltage applications. The variance in architectures, there is more like diesel electric things, there is grid connected units. So from our point of view, it does make sense to create modules that are reusable, but not in any cases to create a pre-validated system solution that tries to cover a large portion of the market. Of course, there is specialized solutions, pre-validated system solutions with partners. We're also working with those guys, and I guess many of you are also doing that. But we're trying to be, let's say, kind of agnostic in the high voltage space and just bring in some modules, pre-validated modules that also work together with partner solutions, like, for example, partners that have high voltage batteries that we do not have, or partner solutions where generators and engines work together. So in this case, baseline message is we need some kind of a platform logic where we have modules that work together with each other across company borders with some pre-validated characters. And this brings me to one of the messages I also want to bring in this presentation. When you look into the market, into that low volume, high variance market that we have now, I think the nice word competition as a word, as a mix of competition and cooperation, is the new normal in that fragmented market that we are in. Because nobody can scale that market alone. We need to somehow find ways to work together. We can't start competing again when the market is there in like 5 years or whenever. And electrification is a no-brainer, but for the time being, I think a lot of us need to work together. And this is one of the messages, or one of the answers to my initial question on how can we help scaling electric off-highway applications. It's when thinking about how to overcome the hype and work towards that plateau of productivity, climb that plateau, then my answers, our contribution to that will be modularity. It's modularity in products, in hardware. I showed the motors example, but also in software, like software modules, and in subsystems. Think about the high voltage space. Pre-validated subsystems can help being fast, can help time to market and saving efforts. But of course, customization is something that is very, let's say, very deeply integrated in our market. So customization is something we need to allow for. It's not just highly integrated systems like automotive, but flexible, modular, pre-validated subsystems that help. And here we need to work together. And this brings me to the last point. Partnerships is something I think that is very important to scale that market. So let me close with probably one practical question for you for your next program review to think about, and that is, which part of your machine truly differentiate and which part should no longer be reinvented when talking about electrification. Thank you for attending the session. I'm looking forward to Q&A and discussion afterwards if there's any interest in following up here. Thank you.
Great. Thank you so much for that, Christian. I think we all took a lot away from that discussion. We do have a couple of questions in the Q&A. I'd like to invite everyone to add further questions as well. But to kick things off, we have a question around preferred voltage levels. Do you think you could speak to that for a minute, Christian? What preferred voltage levels do you see, and what difference does that make?
Well, there is at least distinctive voltage classes, but it's really hard to find a preferred voltage level. And when you talk about small machines, everybody loves that 48-volt voltage level because it's external safety voltage. You do not need to train your service staff, you do not need to train your production staff, and so on. So everybody wants to work with 48 volt, but it becomes unpractical at some time. So there is, let's say, still a large space for 96 volt systems because of cost advantages. But in the end, if the power goes beyond, let's say, 50 kilowatt, 40, 50 kilowatt continuous, then you need to go high voltage. So preference depends always in this market a lot on the application you're talking about. So I think this has been a question that has been around for like when electrification started many, many years ago. And it's still, there is, you see, I've been elaborating on this now for at least a minute. There is still no clear answer because at least the voltage classes I mentioned are, let's say, every class has their advantage or disadvantage. So I think they will coexist over a long, long time.
Great. Thank you for speaking to that. One question we always get here at Bluebotics is about the ROI of the vehicles, the return of investment. So we understand that new technology always requires investment, and you did mention a few figures as we were going through the talk, like the 10% uptick in productivity, for example. Do you find that you get good ROI with this, the scaling, or is that something you could speak to?
As always in these kind of questions, I can just give the unsatisfying answer. It depends. It depends on a lot of boundary conditions. Like, for example, ROI. Maybe the most important thing on ROI is operating hours throughout the year. So talking about, for example, a ground support equipment application like an airport truck or things like this, they have a very high utilization rate up to 4,000 or 5,000 operating hours per year sometimes. And this, of course, brings a lot of advantages when it comes to ROI. That's maybe part of the reason, besides the infrastructure topic, that we see a lot of electric ground support vehicles, and electrification actually is not a question in ground support equipment anymore because of the ROI case probably. But there is also like operating cost, which is expected to be significantly higher with increasing CO2 taxes, with increasing oil prices, which is a hot topic for the time being again. So I think it's like you have to kind of reevaluate that at least once a year when you talk about your machine. What is the actual use case? What is the TCO of an electric part? And at the same time, battery prices are dropping a lot. So I think it's with that range of applications, no general answer possible, but the perspective actually is good on ROIs. Our ROI cycles are getting shorter.
That's a really good point about the shortening of the ROI cycles. We have another question come up in the chat. Again, everyone, I'd like to invite you to add further questions. But where do you see the EPTO, that is the electric power takeoff applications going? So that's as opposed to full drivetrain electrification.
As opposed means,
sorry, go on. So not the full drivetrain electrification in contrast to.
That's what I thought reading out of that question. So this is what I probably refer to, if I get it right, as that subsystems, for example, where you have a conventional truck and you have some electric PTO on that. And I think this is mostly, of course, regularity driven by regularity in the first place. When you have, like, for example, urban areas where you want to have the local zero emission, you want to switch off the truck and operate everything with zero emission. But my experience from many projects we had is like the noise emission thing is the one thing that really makes a difference in the end, because everybody who has been operating such a machine, who has got the feeling that when you, let's say, turn up the power, there is no diesel engine turning up the speed. This is really a nice example. Or just think about electric garbage trucks and things like that. Of course, this is again with electric drivetrain, but EPTOs might be especially when it comes to scaling effects, a big advantage for especially noise emission.
Fantastic. And we've got one more question. I think this might be our last one. But are you seeing more OEMs wanting to own the application software themselves rather than tier ones owning the software development?
Yes, clearly. And I think I've been talking a bit about differentiation. And of course, in a world of software defined products and software defined machines, owning the application software is something that allows for differentiation. So this is the reason why I brought that diesel engine comparison to the pre-validated kit example. Differentiation is not in the rotating shaft, but in the overlying application software that defines on how the vehicle behaves. This is something I think we and also most of our competitors are trying to open for the giving building blocks to the OEMs to be fast, but allowing of course to recombine, to modify those building blocks in order to have differentiation on a software level. I think this is something that is actually really necessary.
Fantastic. Yeah, that makes a lot of sense. So thank you for speaking to that. I think that is all the time we have for today, unfortunately. But Christian, I see you've got your email up on the screen there. If anyone would like to follow up personally, of course you can. And a recording of the session will be sent to all attendees later on. Speaking of, if you're interested, you can view and download a certificate of attendance for continuing professional development credits for live attendees. So, to qualify, you must have viewed the session for at least 75% of its broadcast time, and you'll be able to find them in the event lobby under the feed tab. So I'd like to again say a massive thank you to Christian for your time today and for all our attendees for joining this session. You can join further sessions from the lobby, and we'll see you again soon here in the future of electrification. Thanks all.